Okay, at the end of the first lecture, we showed the condition of equilibrium between phases containing different components. And the instance I used was the reaction of fayalite with quartz to make orthopyroxene ferrosilicate. And we showed that the condition of equilibrium is that the free energy change is zero, and that equals the chemical potentials of the product components. 2 is because there are 2 moles in the reaction, minus the chemical potentials of the reactant components. And that's general. We can treat any reaction, no matter how many different components, no matter how complex, in exactly the same way. We write down the balanced chemical reaction, and we write the chemical potentials of the product reactants always on the the product components on the right, and subtract the chemical potentials of the reactant components on the left, set that to 0, and that gives us the condition of equilibrium. Okay, so now the question is, what is G made of? How do we measure it? We've already talked about it being the sum of the chemical potentials of the constituent components in a phase, but the free energy of a phase is defined as its heat content, or enthalpy, minus temperature times entropy. Okay, so that's the enthalpy, and that's the entropy. And as we've just defined it, the free energy has units of joules per mole. So enthalpy obviously is in joules per mole, and entropy is in joules per mole per degree. Okay, so I think some of us at A level, we did an experiment in which we measured the enthalpy using a calorimeter. Measured the enthalpies of, I think, when I did A level physics, it was a rubber bung, something very simple, using a very simple calorimeter and using Newton's law of cooling to figure out the heat losses that we'd experienced apart from those given up to the calorimeter. Anyway, let's see. So these parameters themselves are dependent on temperature. The enthalpy or heat content increases with increasing temperature, and it has a coefficient of proportionality, sometimes called the specific heat, more normally called the heat capacity. So dH dt is Cp, and that is the heat capacity. At constant pressure. And the SdT is the heat capacity divided by T. So as we raise temperature, we increase both the enthalpy and the entropy, and to quite a significant extent they tend to cancel one another out. But anyway, we'll come to that more clearly in a moment. If we write down a reaction, delta G is equal to the sum of the chemical potentials of the products minus the sum of the chemical potentials of all the reactants and that's equal to the enthalpies of the products minus the enthalpies of the reactants minus T into the entropies of the products minus the entropies of the reactants. Okay, so this is usually given similar, fairly obviously, delta H, and that's given the symbol delta S. Now there are a couple of things to note about this. The first is that enthalpy does not have an absolute value. It is usually measured relative to the it usually refers to the heat of formation of the compound of interest from its constituent elements. So it doesn't have an absolute value, we only have a scale of relative values. Okay? So, if we go and look in thermodynamic tables, everything we see will almost certainly be expressed relative to the constituent elements. So it is usually expressed as the heat of formation from the elements. So, for example, for Fe2SiO4, the enthalpy would be heat of formation from 2 Fe's plus 1 Si plus 2 O2s. Okay, so that's what our enthalpy of Fe2SiO4 would be the heat of formation from 2 lots of metallic iron, 1 molecule of metallic silicon, and 2 moles of gaseous oxygen. Okay, it's a big number usually. Entropy, on the other hand, does have absolute values. And this comes from the third law of thermodynamics, which states that at absolute zero of temperature, the entropy of a pure substance is zero. Okay, so at 0 degrees Kelvin, S is 0 for a pure substance. And so S from ds dt is Cp over T dt, sorry, Cp over T. So the integral from 0 to T of ds is the integral from 0 to T Cp over T dt. It's not a simple integral to do because Cp is temperature dependent itself, but S at T minus S at 0 degrees Kelvin is the integral of 0 to T of Cp over T dt. So C sub P. And the 0 degree value is 0 for a pure substance. So heat capacity Cp can be measured from actually temperatures very close to 0 degree Kelvin up to high temperatures. And so we get the third law entropy, as it's called, that value, from this integral. But basically you measure this down to about 3 or 4 degrees Kelvin with a liquid helium calorimeter, and then you extrapolate to 0. And then you just get the integral under the curve and gives you entropy, third law entropy. Okay, now what about the effective pressure? Again, we can have a definition, which is that dg dp constant temperature is equal to V. Okay? So let's write down let's write a reaction. Let's make it a fairly simple one. Why don't we take this reaction that we talked about before, the reaction of olivine plus SiO2 to 2 FeSO3. So delta G at 1 bar and temperature T is equal to delta H at 1 bar and 298 degrees room temperature plus the integral from 298 to T of delta Cp dt. So delta Cp is the difference in the heat capacities of the products minus the Cp's of the reactants. Minus T into delta S, 298 and 1 bar. Let's do the subscripts the same as before. Plus delta Cp over T dt. the integral of that from 298 to t. And then delta to get delta G at p bars in t, which is what normally we're interested in. We're interested in some high pressure, not just at room pressure. So delta G at P and T will equal delta H at 1 and 298 plus the integral from 298 to T delta Cp dt. So that's the value at 298 degrees K. So this is the value of the heat capacity difference between the products and the reactants, and that takes our enthalpy change up to temperature T minus T delta S at 1 and 298 plus the integral from 298 to T of delta Cp over T dt plus the integral from 1 bar to P of delta V dP, where in exactly the same way as before, delta V is the volumes of the products minus the volumes of the reactants. All right. So, how do we go any further? Well, we can make some simplifications. And that's as follows. For reactions like this one, which is fayalite plus quartz, ferrosilicate, for reactions of that kind, where all the reactants and products are solid, so we have solid only, sorry, let's write that slightly different. So for reactions involving only solids, delta Cp is approximately equal to 0. And delta V is essentially independent of pressure and temperature. Which means if we make that, so what that means is that the delta H here is essentially constant, independent of temperature at 1 bar. Delta S is constant because that's 0, and that's essentially 0. And this is a constant, which makes that integration, of course, trivial. So delta G at P bars and T, to a good approximation, is delta H at 1 bar. I put T. What one tends to do is one tends to average this over some temperature range. So I'll just call it delta H at 1 and T minus T into delta S at 1 and T plus, and the integral here we take delta V outside, So that's a constant, so the integral of dp, of course, is just p between the limits of p and 1 bar. Alright, so it's a nice simple linear equation. And that's why reactions involving only solids form straight lines on a PT diagram. Alright? Because the volume change is essentially independent of pressure and temperature, and the enthalpy is at 1 bar is independent of temperature, and the entropy is independent of temperature. So it's a simple straight line on a PT diagram. Okay, let's take an example. Let's take a different example. I'm getting a bit bored with that one. So I've got some numbers written down. Let's take an aluminosilicate. I've written down the values for this reaction. So the reaction Al2SiO5 and lucite goes to Al2SiO5 sillimanite. And delta H for that reaction at 1 bar and T, average value at T at 1 bar is 3054 joules. And delta S at 1 bar is 2.97 joules per degree. And delta V is minus 1.663 centimeters cubed. Okay. So let's think about units here, because we're working in joules, which is an SI unit. SI unit of volume, of course, is meter cubed. So that's 1.63 times 10 to the minus 6. And what's the SI unit of pressure?
Joules per bar?
No, the SI unit.
Pascal.
Pascal. Okay, so what we can do, if we this is 1 minus 1.63 times 10 to the minus 6 meter cubed, and we can put in pressure in pascals. And 1 bar, of course, is 10 to the 5 pascals. So what I tend to do, because these units are more familiar to people working in geology, is I tend to convert this volume to a unit which is consistent with bars, pressure in bars. And you can see that it's a factor of 10. It's 10 to the 5 here, 10 to the minus 6 there. There's a factor of 10. And so what we do is if we divide this by 10, it then becomes joules per bar. Okay. If we use this as meter cubed and that as pascals, we just get joules. And so now if we use volume, we divide the centimeter cube by 10, get joules per bar, and then we can work in bars. And I think people tend to be very familiar with bars rather than with pascals, because in the Earth you're talking about 10 to the 9, 10 to the 10 pascals, which just it's a lot of messing with zeros. So I'd rather not do that. So what we'll do from now on, we'll use volume in joules per bar. So the question is, what does this line look like on a PT diagram? Okay, so we want a PT diagram. I'll just rub that out. How do we find a PT diagram for equilibrium? What do we find the conditions of equilibrium? Well, we use this equation here, delta G PT is delta H 1 bar in T minus T delta S at 1 bar in T plus P minus 1 delta V. Of course, remember the camels over there, which I haven't up to now. And we set that to 0. So first of all, to get the PT, to calculate the line on the PT diagram, we can say, okay, what's the equilibrium temperature at 1 bar? Okay, so we set P equals 1, so that term disappears. And at 1 bar, 0 is going to equal delta H minus T delta S. T is equal to, put that on the other side, delta H over delta S, which is 3054 divided by 2.97 degrees K. Got a calculator? $1,043. Now it's a straight line, so we could simply calculate it at some higher pressure and just draw a straight line. But there's actually a slightly more, let's say, sophisticated way of doing that. We can just calculate the PDT, the slope. And what we do is, this is delta G at P and T, and we can calculate that delta G at P plus dP, T plus dt. Okay? And since we're on the equilibrium boundary, that has to be 0 as well. So at some slightly higher pressure and temperature, we'll set delta G equal to 0 and calculate the difference between that one at P and T, and P plus dP, T plus dt. So that will equal delta H minus T plus dt delta S plus P plus dP minus 1 equals 0. Alright? So this is one point on the PT line between Andalusite and Slimline, and this is another point at slightly higher pressure and temperature. So we subtract 1 from 2, and we'll get so it'll be minus dt times delta S plus dP times delta V equals 0. Okay, subtract that one from that one. So this goes, that goes with that.
Delta V missing.
I missed the delta V there, thank you very much. Was that all I missed?
I think so.
Yeah.
Sorry. Glad somebody's awake. So, we stick that on the other side, and we get delta V over delta S is equal to dt dP. Oh shit, sorry. Okay. Put that on the other side, divide by that. Sorry, divide by the dP. So it's okay, so that's it. The TDP is delta V over delta S, and that will be in K per bar. So in this case, that is minus 0.163 divided by 2.97, which is equal to calculator.
About 0.54.
0.054.
Something like that. It's just
Yeah.
5.3, bro.
Zero point 0.0549. And that's in K per bar. Sorry, it's negative. So, on the PT diagram, at 1 bar, this intercept is going to be at 1043. So let's say at 5 kilobars, 5,000. Okay, so we're going up at 5,000, T is going to equal 1043, the value at 1 bar, minus 0.0549, which is the PDT, times 4999. So what's that?
$768, I think.
You're actually doing this or doing it in your head?
In my head, it's 5,000 times. The second term is about 275.
Yeah. 769. So that's 500. And at 5 kilobars. I haven't quite drawn it straight, but that should be 769. Okay. Alright, so now all we need to do is figure out which side of the reaction is which. So let's think about it. The free energy change is the chemical potential of AO2SO5 in limonite minus that in andalusite. We're dealing with single component phases, so mu, if you recall, the free energy of the phase is the sum over all I of xi times mu I. And these phases is just one component. So for a one component phase, its free energy is equal to the chemical potential of its one component. Should probably have mentioned that a little earlier, but that's pretty obvious. So the chemical potential of the one component and the free energy are exactly the same. We only have one component. So delta G then, what happens as we raise the pressure? As we raise pressure, delta V is negative, which means that as we raise the pressure, delta G is going to get more and more negative. So do we favour products or reactants?
Lowers the volume of the product.
Yes. So what's happening is, as we raise the pressure, the free energy is getting more and more negative, so which means we're stabilizing the products. Okay. So a negative delta V, fairly obviously, so a negative delta V leads to increasing stabilization of the products with increasing pressure. Okay, I've got, keep that up there. Oh, it's just time consuming. say normally these are good breaks for people to answer questions, but people. All right, so delta G P and T is equal to delta H minus T delta S at 1 and T plus P minus 1 delta V. So, as we raise pressure, if delta V is negative, increasing pressure makes delta G more negative. Which means you're stabilizing the products. Okay? So free energy of the products becomes progressively lower relative to the reactants. On the other hand, if delta S is positive, then increasing temperature will favour the products as well. So if that's positive, increasing T will make this more and more negative, which will stabilise the products. If delta S is negative, increasing temperature will do the opposite. So if delta S is negative, increasing temperature makes delta G more positive, stabilizing reactants. So, if delta V is negative, increasing pressure favours products. If delta S is negative, increasing temperature favours reactants. And the opposite is true as well. So if delta V is positive, increasing pressure stabilises reactants. If delta S is positive, increasing temperature stabilises the products. So what we have here not sure that we can see all the board now. What we have is andalusite goes to selimonite. So delta V is negative and delta S is positive. So this is minus 0.163. And that was plus 2.97 joules per K. So what this says is that increasing pressure favours selimonite, increasing temperature also favours selimonite. And our PT diagram looks like this. So increasing pressure favours selimonite. So if we go this way, we go to selimonite, and if we go in increasing temperature, also favours selimonite. So that is the selimonite field. And this is the field of andalusite. Andalusite. Okay, so it looks like so. It's not the complete diagram yet, but you get a chance to calculate that in practical. Okay, now I just wanted to do one last thing in this lecture. And I wanted to talk about Hess's law, which again many of you will have heard of in either chemistry or physics. at A level. So we've got delta H, delta S, delta V. Normally we can just go and look these things up in tables. Or somebody might have written a nice convenient computer program to do it for us. Well, let's take Hess's law. And what does that do for us? Well, it tells us that enthalpy, entropy, and free energy depend only on the state of the system. They depend only on the pressure, the temperature, and the composition. They don't depend on the path taken to reach that state. Okay? So, enthalpy, entropy, volume, free energy depend only on the state of the system. I.e. the pressure, the temperature, and the composition. Not on the path to that state. Well, that all sounds very arcane. What the hell does it do for us? Well, what we can do, what it means is that these parameters, enthalpies, entropies, volumes, are all additive. Can be added and subtracted to one another at will. I should give you an example. Let's suppose we're interested in the reaction of graphite to diamond. Okay. Diamonds being rather interesting capsules bring out material from the interior of the Earth, apart from being rather loved by certain people for jewellery, but they are nice inert capsules that bring up minerals actually from the deep interior, from even below the 660 kilometre discontinuity. We find some minerals in diamonds which have come from beyond, from deeper than 660. How do we know that? Well, it's because they're only stable at pressures deeper than 660 kilometres. And there they are, sitting in diamonds collected at the surface. Okay, let's suppose we want to know, we're interested in the reaction graphite goes to diamond. So the reaction, nice simple reaction, carbon and graphite goes to carbon in diamond. Actually, I'm going to write it the other way around. Don't know why, I just feel like it. So we write it diamond goes to graphite. And that has an enthalpy change which I'll call delta H1, which is equal to obviously the enthalpy of carbon in graphite minus the enthalpy of carbon in diamond. Now I could get some diamond and heat it in a calorimeter and what's its transformation to graphite and measure the heat given out. But actually, the reaction is so slow, it would take a lifetime to get any results. And people don't have the patience to do that. You won't get too many grants to do that sort of experiment. So what do we do? How do we know the enthalpy of this reaction? Well, we use Hess's law. So what that says is, what you do is you go along to De Beers or one of the large diamond companies and ask them to give you some diamond. And then what you would do, you would burn it in your calorimeter. So you'd react it with oxygen. And make carbon dioxide. Now that reaction goes pretty fast. And we can measure that enthalpy using a calorimeter. And then you would take some graphite and do the same. In this case it's cheap, it doesn't require a fancy grant from De Beers. And measure that enthalpy, which again will be different. And then what you do is you subtract this one from this one. So what happens is if we subtract this reaction from that reaction, we have carbon diamond plus O2 minus carbon graphite minus O2 equals CO2 minus CO2, and the enthalpy is delta H H2 minus delta H3. That's what Hess's law tells us. We can add and subtract them. And what this means is that if we cross out things which disappear, is we just have C diamond minus C graphite equals 0, or C diamond equals C graphite. And that's what we wanted at the beginning. Delta H1. So delta H1 is that one minus that one. In words, what we've done is we've taken diamond, turned it into CO2, taken our CO2 and turned it back into graphite. That's what we've done in words. And that's that enthalpy plus and that enthalpy minus here. And what we end up with, of course, is what we wanted, which is diamond versus graphite. So all of these so-called functions of state, enthalpy, entropy, volume, are additive like that. So we can get, it doesn't matter, the path is irrelevant. It only depends on what we start with and what we end with. Okay, I'll do it.